The last time, or in the first lecture, we talked about the escape velocity, orbital velocity. Sorry. So you remember this diagram here, this figure here. Is the velocity at which if you throw an object, it will keep orbiting around the Earth. That velocity is called the orbital velocity. And while you are in the before it is before it hits the ground, and if you measure the weight at any point here, it would weigh nothing. It's in a free fall state. It is constantly falling freely under gravity. That is called a weightlessness condition. So whenever there is like a satellite orbiting around the Earth, it's a free fall condition. If you are onto a scale, onto a satellite, you would weigh nothing. You would weigh zero because it's a weightlessness condition. It's a free fall condition. There's no normal force. Now we'll talk about the angular momentum. So far, why we talk about the angular momentum? The motion can be either in a straight line or it can be in a closed loop or in a curved path. For example, here, as talked about, like the motion can be either in a straight line or it could be in a circular orbit or in an elliptical orbit. If I'm moving in a straight line like this, then I'll talk only about the linear motion. But now if you're moving in a closed orbit or in a circular orbit, then you'll talk about the angular momentum. In this case, when it is moving in a straight line, then you will only talk about the linear momentum. Here you will talk about the angular momentum. The formula for the linear momentum is simply called P is the linear momentum is the mass times the velocity. The angular momentum is usually denoted by L, and it is defined as the mass times velocity times r. And what is r? R is the radius. Okay, so this is the angular momentum. And we talk about the angular momentum when it is moving in a circles or spinning. All right, so here is the summary that we learned so far. The speed is defined as the distance over time, and the speed with the direction is called the velocity, and the acceleration is defined as the change in velocity with respect to the time. If there is a change in velocity, there must be an acceleration. The momentum is defined as the mass times velocity. Okay, this is the linear momentum. Again, this momentum is the linear momentum. That means the momentum in a straight line. The force, the formula for the force is equal to the mass time acceleration. This is the acceleration. And angular momentum, I'll just write it down here. The angular momentum is defined as the mass times velocity times radius. How do you know that this mass times velocity is simply the linear momentum? Okay, so this is so far what we learned. We also talked about the mass is the quantity of matter, and the weight is a vector quantity which depends upon the acceleration due to the gravity. If I need to write down the formula for the weight is simply equal to the mass times the gravity. And if it is in a free fall state, it weighs nothing. It's zero. We'll talk about the Newton's first law of motion now. It's a pretty straightforward law of motion. if an object is moving in a straight line with a constant velocity, it will keep to move in a straight line with the same velocity until some force acts on it to stop it. And if it is at rest, let's say if a particle is at rest, it will be at rest until some force acts on it. That means if I'm moving with a 50 mile per hour, I will keep moving with a 50 mile per hour until some force acts on it. If there is no force, I will keep moving. While you drive a car, and even if you don't apply a force, it comes to a rest because there is friction force. It is the friction force that is bringing the car to a stop, even if you do not apply the brake. Otherwise, if there were no friction force, once you moving, let's say with 20 mile per hour, it would keep moving with 20 mile per hour forever if there were no friction force. And let's say I have a glass here in front of me. If I do not apply the force, it will be here forever and ever because there is no force acting on it. If I apply a force, only then it moves. So a force does change the position of the object. It can move from, if it is moving from a constant speed, it can bring it to, it can change the speed. Or if it is starting from rest, it can move, it can give it some velocity. That's what the force can do. So the force is equal to the mass times acceleration or rate of change of momentum. So there are two definitions of force. That is exactly the Newton's second law of motion. The Newton's second law of motion is simply tells you the force is simply equal to mass times acceleration, and this is the rate of change of momentum. Remember, the momentum again is the linear momentum. Momentum is simply equal to the mass times velocity. Okay, if there is a change in velocity, then that means there must be some force acting on it. What is the Newton's third law of motion? It says to all action there must be an equal and opposite reaction. So here you see the rocket. A rocket is just based on the Newton's third law of motion. In this case, the rocket is propelled upward. So when it is expelling the gas outward, the gas is also expelling, is applying a force which is upward, and that's how it is propelled forward. If I hit onto the wall hits back to me exactly with the same force. If I hit onto the wall, I'm applying the same amount. If I'm hitting the wall with a 10 Newton, the wall hits back to me exactly the 10 Newton. So it's exactly equal and opposite force. That's what the Newton's third law of motion is. Now, a third question for you now. So, how does the force the earth exerts on you compare to the force you exert onto it? By Newton's third law of motion, the force should be exactly equal and opposite. So the answer is pretty obvious here. It just comes from the Newton's third law of motion. If I apply a force onto any object in the universe, that object also applies a force to me with exactly equal force. So now we'll move to the talk about the circular orbit motion that we define with the angular momentum. Now you remember the linear momentum formula. Linear momentum, now we call just to separate it, or we just simply call the momentum. The simply momentum is defined as what we call simply momentum, or the linear momentum 2 is defined as the mass times velocity, and the angular momentum is defined as the mass times velocity times the radius r. Okay, here is the example. Here you have the sun here, and this is the earth, and the earth is moving in an elliptical orbit. So here the angular momentum at any point is the mass times velocity times r. Okay, now let's say the earth comes to this position here, and it is moving in an elliptical orbit. Here if I compare, if there is no any external force acting onto the system, the angular momentum would not change. It would be the same thing. So that means if I look at this point, the r is smaller. That means it moves faster here because the angular momentum does not change. In this case, the radius, the distance compared to this point is larger. If the radius is larger, then the velocity has to be smaller. Okay, so the velocity in this case is smaller. Why is that again? Because the angular momentum has to be conserved. If I measure the angular momentum at this point, mvr, and mvr at this point, it has to be exactly the same. Mass does not change. You see that radius here is greater, so the velocity has to be smaller. In this case, radius is smaller, so the velocity has to be greater. But the product mvr, it doesn't matter where you measure, it's exactly the same thing. Okay, so if there is no any external force acting on it in circular orbit or in an elliptical orbit, the total angular momentum remains constant. So even when the earth is moving around the sun, the linear velocity of the earth does changes. It does change slightly bit from the summer to the winter. When it is away from the sun, it moves a little slower. When it comes closer to the sun, it moves a little faster. Okay. So what is angular momentum? It is a mass times velocity times radius. Again, as I said, nothing can change itself unless you apply some force. Nothing can change. If an object is moving into an orbit, for example, the earth is moving around the sun, it will keep moving forever and ever and ever until some external force or torque acts on it. Now, I will just give you some beautiful example. All of you know about the ballet dancer, the spinning, sometimes faster, sometimes slower. It's just based on the concept of the physics, which is called the conservation of angular momentum. You know that. What is the angular momentum now? What the angular momentum is simply the mass times velocity times the radius. The angular momentum. For example, the dancer here. See the dancer here. If you look and she is spinning, or she is spinning from her axis, and this is the radius here, r. So the angular momentum is m times v times r. In this case, a radius is greater, so she spins smaller. But in this case, when she brings her arms back, the radius r is small. R is small. So that means it spins faster. Spin faster here. Why is that? Because she has brought her arms closer to her body. That means the R is smaller. If R is smaller, so if you just look at this formula here, if R is smaller, mvr, R is smaller, that means the velocity would be faster. Okay, so in this case you would spin faster because our r, in other words, we call the moment of inertia. We're not going to cover here. In this case, when you bring your arms close to your body, your r is small. That means your velocity has to be larger just to keep MBR constant. Now we'll talk a little bit about the universal law of gravitation, or Newton's laws of gravitation. What is the Newton's law of gravitation? The Newton's law of gravitation is simply equal to G. If let's say you have two objects here, M1 and M2. Any object, any mass within the universe attracts other masses. And the force of attraction is equal to G times M1, M2 over distance squared. And M1 is the mass of the first object, M2 is the mass of the second object, and the distance squared. If the distance is greater, the force of attraction is smaller. And this G is called the universal gravitational constant, and it is constant, doesn't matter where you are. And remember, this G, the capital G and the small g, are two different quantities. It's not the same thing. The value of this G, the small g, is simply equal to 9.8 meter per second square. This is acceleration, and the value of this G, the capital G, I'm just writing down here, this is equal to 6.67 times 10 to the negative 11 Newton meter square per kilogram square. Okay, I'll just escape these things here. Okay, now we already talked about the angular momentum. Now we'll talk about the escape velocity. What is the escape velocity? This is a wonderful concept again. Now let's say you want to go away from the earth. How would you go that? Doesn't matter, like if you try to throw an object from the earth's surface, it comes back to you. And if you throw higher and higher, it goes further, but it again comes back to you. So remember, when you talked about the orbital velocity, if you throw an object at a certain velocity horizontally, then it may keep, if you have enough speed, then it may keep moving into an elliptical orbit or circular orbit. But now, if you throw with a much higher speed or the velocity, what will happen? It will leave the Earth's surface, and it leave the Earth at the gravitational field and go into the solar system, or it may go somewhere. That is called the escape velocity. That means why we call the escape velocity, because it is now going away from the Earth's gravitational field. And the escape velocity for the Earth is equal to 11 kilometer per second. What does it mean? That means if you move 11 kilometer in 1 second, you may go out of the Earth's gravitational field, which is equal to 40,000 kilometer per hour. While you're driving a car, you're driving only about the 60 kilometer or 100 kilometer per hour. Now, let's say, for example, you design a car. You design a car, or you design a rocket or something. And all of a sudden, now you start moving with the 40,000 kilometer per hour. You will go out of the Earth's gravitational field. That is called escape velocity. Okay, even the Earth's gravitational pull is not strong enough to bring back into its orbit or onto the Earth's surface. You have sufficient energy just to break down the Earth's gravitational field, and now you're going into the solar system, or you're going somewhere into the cosmos. All right? Okay, we'll talk about the tide now. So it's a pretty simple concept here. We know from the Newton's law of gravitation, if you have two masses, they attract each other. I'm attracting you, you attracting me, the wall is attracting towards me, I'm attracting towards the wall. Everything around you attracts each other. That's the Newton's law, universal law of gravitation. It doesn't matter where you are, there is always the Newton's law of the gravitation. So the Newton's law of gravitation holds everywhere into this space. And here we're going to only talk about the gravitation between the Earth and the Moon. And it has so many effects onto the Earth's surface, and you can see it. And you also remember the formula for the Newton's law of gravitation, that it is dependent on the distance between the Earth and between the two objects. For example, the distance between the two objects doesn't matter. What's the force of attraction between the two objects? So this is the Earth here, and this is the Moon, and the shaded portion represents the ocean. Now here, the distance is comparatively, if I look at the two locations here, if I compare the two locations, the force, the gravity does change depending upon the location. The gravity attracts Earth and the Moon towards each other, but it is different at the different locations on the Earth. It's slightly different because the strength of the gravity decreases with the distance. The gravitational attraction of each part of the Earth to the Moon becomes weaker as you go from the side of the Earth facing the Moon to the side facing away from the Moon, which means if I am at this location onto the Earth's surface here, and if I'm here, the force of gravitation at this point and this point is different. It is stronger here and it is weaker at this point. So this difference in attraction creates a stretching force that we call the tidal force. That tidal force stretches the entire Earth to create two tidal bulges, one facing the Moon and one opposite to the Moon. If you have, let's think this way, let's say you have a rubber band. If you pull one side of the rubber band, the other side of the rubber band is also stretched. It's not like that you stretching in only one side. If you have a rubber band, you just try to stretch it. When you stretch it, both sides are stretched. So the tidal force is greater. So the force of attraction is greater here than here. So the difference in the gravitational attraction causes the two tidal bulges. And these two tidal bulges are exactly on the opposite sides of the Earth. Okay. Now, the tidal affect both land and the ocean, but we generally notice only the ocean tides because the water flow more easily than the land. Earth's rotation carries any location through each of the two bulges each day, creating two high tides. So you have two high tides every day, depending on the location. Low tide occurs when the location is at the points halfway between the two tidal bulges. So in this case, so you have the high tide at this point and at this point, and you have the low tide at this point and at this point. Okay, so when the sun also has small effect onto the Earth. If you have the moon, sun all lined up together, and you see the sun is also attracting towards each other, in this case all are aligned in the one direction, so you see the high tide effect. But when the moon and the sun are at 90 degree, for example in this figure, then the gravitational force due to the moon is more than to the sun, so you'll see the tide effect along this direction. And compare to this particular orientation, this orientation has a weaker tide. This is called the spring tide and this is called the nip tides. Okay, all right. So and you will see the high tide during the new moon and the full moon, and you'll see the low tide during the third quarter of the moon and the first quarter of the moon, where the sun and the moon are about the 90 degree, or the force of gravity between the earth and the sun and between the earth and the moon are at 90 degree. I will not talk about the tidal friction. For those who are interested, um, I'll post a separate video about this tidal friction. This is not required for this class, but if you're interested, ask me any question if you have. So far, what you learned now? So we talked about the gravity, the Newton's laws of gravity, the gravitation. We talked about the what causes the tide, the moon's gravity, the gravity between the moon and the earth is different depending upon the location that causes the tide, and all the objects fall at the same rate. So that's all I've covered today. And if you have questions, any questions, do not hesitate to ask me. All right, thank you, and I wish you all the best for the homework too. Again, any question with the homework, just write to me. Thank you, and have a good one.